Hello learners, I am Dr. Manish Kumar Bhardwaj from School of Engineering and Technology of IGNOU. In our last discussions, we discussed about the repairing materials for timber, for steel and also for sanitary fittings. Now we are moving to repairing materials for miscellaneous defects. You know that defects in buildings can be attributed to the deterioration of the individual materials or components of the structure. The materials include structural steel, reinforcing steel, pre-stressing steel, timber, bricks, stones and most important of all, concrete. You know that we have already discussed about repairing material to attend defects in timber, steel and sanitary fittings. Defects other than those specifically covered already are to be classified as miscellaneous defects or deterioration. We will now be dealing with this subject with a particular reference to concrete, the most important construction material that you know. The aim of this lecture is that after going through this lecture, you should understand the various type of cracks. You should also be able to analyze the causes of cracks. You must know the remedial measures to treat the cracks and explain various repairing procedures to rectify the various miscellaneous defects. So let us begin with what is deterioration. Deterioration includes cracking, scaling, spalling and delamination. So if any of these things is there, so we will call that deterioration has occurred. So we will deal one by one. First of all, cracking. What is crack? A crack is an incomplete separation of concrete into one or more parts to have a variable depth, but visible at the surface. Plastic shrinkage cracks result from rapid drying of the concrete in its plastic state. Map cracking. Map cracking is a term describing a network of closely spaced cracks that are usually due to chemical reactions between the mineral aggregates and the cement paste. Then next is drying shrinkage cracks. Drying shrinkage cracks result from the drying of restrained concrete after it has hardened. So during that hardening process there may be shrinkage, and due to this shrinkage the cracks may occur in the concrete, and these cracks will be called as drying shrinkage cracks. Then there may be settlement cracks, and these settlement cracks may result from the settlement of the formwork as well as from settlement of the foundation. So if settlement of either of formwork or foundation is there, it will cause cracks in the elements of the structure, and these cracks will be called as settlement cracks. Then there may be some other crack like structural cracks. Structural cracks result from under reinforced or over stressed tension zones in the concrete. Corrosion induced cracks are also there, and these cracks are caused by corrosion of reinforcing steel within the concrete. Much surface cracking seems primarily due to volume changes in concrete caused by poor construction practices, such as concrete that is too wet or placed too slowly or poorly finished or improperly cured. So because of these reasons there may be cracks in the concrete. Second is scaling. What is scaling? Scaling is the process of flaking away or disintegration of the surface mortar of concrete, exposing and eventually loosening coarse aggregate. A weak surface layer of mortar may result from poor finishing and curing practice. If finishing as well as the curing is poor, so it will result weak surface layer of mortar. Scaling is caused primarily by freeze and thaw action. Then next is spalling. Spalling is more serious and more common than cracking. The predominant cause is corrosion of reinforcing steel in the concrete. Spalling is local disintegration of a portion of the concrete surface. So it is different from cracking. Next is delamination. Delamination is a form of scaling which occurs over large area of corroding reinforcing steel rather than being localized over a few reinforcing steel bars, and it results in a plane of separation within the concrete immediately over the plane of the reinforcing steel. So means layers are separated. So that way it is called as delamination. Now let us look at the classification of cracks. Cracks in buildings are of common occurrence, you know. Building components develop cracks whenever stress in the component exceeds its strength. Stress in a building component could be caused by externally applied forces such as dead load, live load, wind load or seismic loads, or it could be induced internally due to thermal movements, moisture changes, chemical action, etc. So these may cause the internal stress. Cracks could be broadly classified as structural cracks and non-structural cracks. Structural cracks are those which are due to incorrect design, faulty construction, overloading or settlement of foundations, and these may endanger the safety of buildings. Non-structural cracks are mostly due to internally induced stresses in building materials, and these generally do not directly result in structural weakening. Vertical cracks in a compound wall due to shrinkage or thermal movement and plaster cracks come under this category. So this is the difference between the structural cracks and non-structural cracks. Though non-structural cracks do not endanger the safety of a building, but they give bad appearance or also may create an impression of faulty work. If you are looking at the non-structural cracks, so it may give an impression that workmanship is bad or it's a faulty work, or also may give a feeling of instability, that looking at the cracks you may feel that the structure is unstable. So these are some psychological effects. Some typical examples of these cracks I will show you here in different figures. First of all, let us see crack due to tension. So here you will see a crack due to direct tension, that is tensile crack in masonry wall. So in figure 1 here you see the tensile crack in the masonry wall. Second type of crack you see here in the figure, flexural tension crack at lintel level due to shrinkage and contraction of slab. So figure 2 here shows you the flexural tension crack at lintel level due to shrinkage and the contraction of the slab. Third type of crack you see here in this figure 3, that is shear crack at corner of wall B due to the expansion of wall A. Here in this figure you see two walls, wall A and wall B. So here you see the shear crack at corner of wall B due to expansion of wall A. Then in figure 4 here you see the shear crack in masonry pillar due to expansion of RCC beam. So, here due to the expansion of the RCC beam, cracks are there in the masonry pillar. Next, in figure 5 here, you see cracks by the side of door frame with wall surface on both sides. So, carefully look at these cracks. Then in figure 6, you see here the cracking due to expansion of brick wall. So, here the cracking occurred due to the expansion of the brickwork. Next is in figure 7, you see here the cracking in topmost story of a load bearing structure. So, look the figure carefully, that how the cracks has developed. Look carefully how cracks have developed in the topmost story of a load bearing structure. Then in figure 8, you see here the horizontal crack at the base of brick masonry parapet support on a projecting parapet. There is a projecting parapet, and on that there is a brick masonry parapet, and here you see a horizontal crack at the base of the brick masonry parapet. Then in figure 9, you see here vertical crack in multi-story buildings having window openings in load bearing walls. Wall marked as A act as pillars and are stressed much more than the portion B marked, resulting differential stresses. So, here some portion is much stressed in comparison to the other, and due to this there is a differential stresses there, and due to that vertical crack are there in the building having window openings in load bearing walls. Then we move to next figure, that is figure 10 here, and in this figure look the figure carefully. In this figure what you see, vertical crack at junction of RCC column and brick masonry. So, here you find a vertical crack at the junction of RCC column and brick masonry. Then we move to figure 11, which shows you a vertical crack in brick wall panel of framed structure due to expansion of brickwork. There is expansion of brickwork, and hence a vertical crack occurred in brick wall of the framed structure. Now we move to figure 12, which gives you cracking of a partition wall supported on RCC beam when length to height ratio is large, and also there is a central door opening. So, here you see a cracking of a partition wall which is having central door opening. So, these are different graphics showing you different type of cracks in different elements of the building. Now, let us move to that what are the causes of the defects or deterioration in buildings. Defects or deterioration in any structure is dependent on the type of structure, how it has been designed and detailed, how it is constructed, how it is maintained, and also what is its environment, because environment of the structure plays an important role in its deterioration. If it is a normal environment, then deterioration will be less. If the environment is aggressive, then deterioration will be more. So, these are different factors on which the defect or deterioration of any structure depend. The common causes are similar regardless of these factors, which primarily influence the degree and extent of deterioration. Causes may be classified on the basis on material of construction, that what material you have used. So, depending on that, various causes may be classified. The causes of cement concrete deterioration include alkali aggregate reaction, unsound cement, contaminated water and aggregates, sulfate attack, corrosion, freezing and thawing, etc. So, these are the different causes for deterioration of cement concrete. Let us see what are these. Let us first look at alkali aggregate reaction. Reaction in concrete between alkalis from the cement in the concrete and reactive components in the aggregates is termed as alkali aggregate reaction. These are believed to be three types. First is alkali silica reaction, then alkali silicate reaction, then alkali carbonate reaction. They can cause cracking and occasionally significant weakening of the concrete may occur. The alkali silica reaction is the most common. Alkali silica reaction can cause substantial reductions in the engineering properties of concrete. For example, at 0.1% expansion, compressive strength decreases about 12%. Loss of flexural strength can be about 50%, and the elastic modulus is reduced approximately by 20%. Now we move to unsound cement. Portland cement as a hydrated paste is the binder of concrete that you know. This binder governs most of the properties of the concrete. Cement is available in several types with and without air entering agents to meet various construction requirements. For example, early high strength and for compatibility with certain type of aggregates. Because of differences in raw materials, cements ground to the same fineness can have difference in strength, heat of hydration, reduction of latence, bleeding tendency and durability. The alkalis in the cement can react with minerals in the aggregate, resulting in cracking and expansion of concrete. Sulfates in groundwater and in soil against which concrete is placed can also react with chemicals in the cement, resulting in disintegration of the concrete. Now let us see contaminated water and aggregates. Means if water and aggregates are contaminated, then what can happen? The usual rule regarding mixing water is that if it meets the requirements for drinking, it is satisfactory for making concrete also. Mixing water can be contaminated by impurities such as sodium and potassium carbonates and bicarbonates, sodium chloride, sodium sulfate, calcium and magnesium bicarbonates, calcium chloride, iron salts, sodium iodate, phosphate arsenate, borate, sodium sulfide, hydrochloric acid, sulfuric acid, then sodium hydroxide and other such salts, and also suspended particles present in the water. It can also be contaminated by algae and other organic minerals. Minute concentrations of contaminants are usually tolerable, and their numerical limits on concentration of different impurities are given in the code. Now move to reactive aggregates. Aggregates for concrete are generally inert. However, aggregates can contain minerals which react unfavorably with the chemicals in the cement paste. These reactive components of aggregate include calcium, magnesium, silica and iron oxide, ferrous sulfides, calcium sulfate, zeolites, clay minerals and dolomitic limestone. So these are the reactive components of the aggregates which may react with the cement. Now, let us move to sulfate attack. Sulfates in groundwater or mixing water or in soils against which concrete is in contact can react with the cement paste in concrete and result in disintegration of the concrete. The problem is sulfates of sodium, magnesium and calcium can react with the cementing constituents of the concrete. Depending upon the composition of the cement, these chemical reactions may be accompanied by large volume changes in the concrete. And you know that volume change in concrete is detrimental because it can cause cracks and the deterioration of the concrete. Now, next we move to corrosion. Concrete can corrode when it comes into contact with both organic and inorganic acids. Organic minerals include acetic acid, oxalic and dry carbonic acids, carbonic acid in water, lactic and tannic acid and vegetable oils. Inorganic acids include the sulfates and chlorides of magnesium and calcium. Corrosion can also be the result of environmental action by wind and rain. Then next is freezing and thawing. Disintegration of concrete is also caused by the disruptive action of freezing and thawing. What is freezing and thawing? Means when water in the pores of the concrete freezes, then this action is called freezing. The problem is that you know that when water freezes, volume increases and it applies stresses on the concrete. Then on heating, when the temperature is high, this frozen water then melts, then this is called thawing. So now the stresses are released. So that way freezing and thawing causes stresses in the concrete. Dry concrete with or without entrained air is usually not damaged by freezing and thawing. Frost also has a destructive effect on a weak and porous concrete. The severest conditions for frost action arise when concrete has more than one phase exposed to the weather and is in such a position that it remains wet for long periods. Alternate wetting and drying has also an adverse effect on the concrete. Then fatigue damage of reinforced concrete is dependent upon both the fatigue life of the reinforcing steel and of the concrete. As for all fatigue damage, the number of cycles of stress and the stress range are the most important parameters affecting fatigue damage. Failure of concrete under repeated loading results in progressive microcracking of concrete. Because there are no plastic deformations to blunt micro cracks, concrete does not have an endurance limit analogous to that for steel. Research on concrete deterioration indicates that fatigue damage of concrete may be more prevalent than it is realized. So, this way we discuss about the various causes of the damage and deterioration of concrete. I hope you must have enjoyed this discussion. So, thank you.